Hey guys, welcome back. In this video, I mainly want to talk about moving average versus normal averaging. So I want to see, which is the better one to use for channel estimation. Okay. So in the previous video, we were talking about how to perform the channel estimation, and we had pretty much, a few solutions. So I will just take y is equal to hx plus n. So this is across single subcarrier. Okay. So the approach was we need to first correlate with the DMRS, right? So y into x star. So I would get something like this, right? So now if you see, this is the error, right? We want only edge, but this part is the error. We need to reduce this error, right? So now I will take the OFDM grid. Mm, so let's say at the third symbol, I am going to transmit the DMRS. So what did we have? According to GPP spec, what was I mentioning in the previous video? So I was telling that, an alternate RAs, we will be transmitting the DMRS, right? So let's say like that, we have some, 50 subcarriers. Okay. So now one of the assumptions which I was mentioning is what if we assume that channel is constant across these 50 subcarriers. Okay, so then in which case what happens? Let's say this is at the first subcarrier. Let us say that it's not exactly 50 subcarriers. For our algorithm, maybe let's say I will fix some 25 subcarriers. Okay, so 25th subcarrier I will have y25 x25 star h plus n25 x25 star, right? So this is the error. So now you perform the averaging across these because h is constant, right? So now if you perform the averaging across it, you can get h at so h plus um, this n1 x1 star plus up to n25 x25 star divided by you will get 25. Okay, so by this way you can reduce this error or noise to a greater extent, right? But as I was mentioning, channel need not be constant across subcarriers, right? That is when I was considering the high speed scenario. So under these conditions, when we take this OFDM grid, okay, so y1 is equal to h1 x1 plus n1, right? So then y2 is also different, okay, because high speed we will have a Doppler effects, and because of which we may not be having the same channel across the subcarriers. Under these conditions, I was mentioning, okay, if we take the first equation, y1 x1 star is equal to h1 plus n1 x1 star, right? So we have this error. This error is a little bit significant, and in fact if you consider even the interference and all, this will be significant. We need to definitely reduce it. Okay, now to do averaging we have some little bit problem here because the channel is not constant. Okay, h1 and h2 are not constant to perform the uh, averaging here. Okay, so I will take the grid over here. Okay, what I will do, um, so across these alternate arrays, okay, we have this one. Let's say this is let's say 10 subcarrier. Okay, for now just assume that this is 10 subcarrier. Okay, so then which means I have y10. Okay, y10 x10 star h10 plus n10 x10 star, right? Now the thing is that since we are not considering the channel is constant, we can make a little bit more relaxed assumption. Okay, that assumption is based on I will just tell it here. See, when on the first subcarrier I am saying that the channel is constant. Okay, on 25th subcarrier also I am saying the channel is constant, right? So let's say this is 25. This is like 1 2 3 4 up to goes 25. Now if I say h here, this also I'm considering edge, which means let's say this is a little bit far right for distance, and there could be a possibility that this channel might not be same. But let's say I will consider some edge. Okay, let's say at 4 subcarrier I have considered edge. This edge will have more closer more closer values with fifth subcarrier, sixth subcarrier, seventh subcarrier, and even in the bottom like third, these subcarriers, right? Basically, what I mean to say is around this fourth subcarrier, we can expect the channel is constant. Okay, almost. So not exactly constant if it is a high speed scenario, but there are chances. We can say that it is pretty much closer. Okay, but definitely this fourth subcarrier will not have much similarity with the 25th subcarrier channel estimate. So considering this, okay, considering this kind of legacy or normal averaging is not that good. Okay, so then, so what do we need to do? There comes the concept of moving average. Okay, this will be more accurate, and this is I would say fairly good assumption to go for. So I will take the OFDM grid. Okay, let's say this is 10 subcarrier. Now, whenever I am calculating, so first, as per our high speed equation, across each subcarrier we can perform these kind of estimates. So now I will say that I would have got channel estimation H1, H2. I mean this is H10, like that it goes on in the H25. Let's say I have all these channel estimates now, but this channel estimation has a significant error here. So we are now going to see how to reduce this error using moving average. So the moving average concept is when you are dealing with the to estimate more refined H10, then what you need to do is you keep a certain window in the moving average. So that window is around this H10. You will take, let's say, for example, six subcarriers, six subcarriers on the upper side, six subcarriers on the lower side. Okay, and you perform the average of these two and put it back in this H10. So what does it mean? Like it means that you will take um, 16. Okay, so H16 plus da 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 plus till H11 at, okay, plus you can even include this H10 plus these 6. Okay, so this is H9 at plus, so H4 at. So there are total 11 samples, you can say divide by 11. All right, this will be morely this will be fairly good assumption to proceed with, and it will give, I think, much better estimates even under a high speed scenario. Okay, so when you go to 11th one, so again 11th one, how you have to do? You have to take 6 above, 6 below, and then you should average it. Okay, so for each and every subcarrier location, you will keep that as the center, and you will take 6 subcarriers on the left side, six subcarriers on the right side, and you are going to perform the averaging. And by that way, these errors, okay, these errors are going to reduce. I think you got a clarity over here. One point to note down is that how to choose this window. Okay, so right now I have just taken 6 on the right side, 6 on the left side, but definitely you might say that I would like to take more. Okay, because to get more accurate channel estimate, but that will again bring in the assumption that the channel will be constant for more number of subcarriers. That is one thing. And second one is when you take more number of subcarriers for averaging, this is going to increase your signal processing time. So you need to definitely make a clear trade-off between the higher signal processing time and as well as your assumption of constant channel estimates. and also the trade-off with the accuracy with which you need to get. Okay, so considering all these trade-offs, you need to design your moving average algorithm very neatly. Okay, this you have to do by performing the simulations either in MATLAB or in some Python, and checking the performance with respect to bit error rate. Okay, but I hope you just got the clarity that okay, what is moving average, how to perform the moving average, and you also got to know that there will be a window across which you can assume that the channel is constant. So if you're looking for more videos, please do subscribe to the channel. Thank you very much. Have a great day. Bye bye.